Hi all, welcome to my second lecture. This is on measurement of high voltages using electrostatic voltmeters. The electrostatic voltmeters, this topic is covered in two parts. This is the first part and the second part will be in the next video, that is video lecture number 3. So in the based on the last video lecture, I myself have observed and then I got some feedback from my students, and then based on that there is a difference between live classroom lecture and then a video lecture. So what is missing is the one-to-one interaction is missing. So keeping that in mind, I want to make some changes in the style of presentation, which includes asking some questions in between. So I have put some questions here and there. So wherever such questions occur, I suggest you to pause a moment and then think about the answer and then start watching the video. So with that change, then other than that, in this presentation, because here the concept need to be understood completely, so some animations I have tried, that is why this lecture got delayed. So yeah, so please watch the lecture. This lecture is dedicated to my parents and all my teachers, and special thanks to my wife and children for making it happen. So in the previous lecture, we have covered spark gaps, including sphere gaps, uniform field gaps, rod gaps, etc. And these, among these sphere gaps are recommended by standards for calibration and measurement purposes. Now, from now on, we will study other types of measurements, including routine measurements and sophisticated measurements for research purposes, etc. And this lecture is devoted to understand electrostatic voltmeter. I tried my best to cover, with as much material as possible and in brief and to make it crystal clear the concepts. So I tried my best to keep everything in the presentation. So what is the basic principle of electrostatic voltmeter is given here. You can see two examples are also given here. So Coulomb's force of attraction between a fixed plate, in this case this is the fixed plate, in this case this is the fixed plate. So between the Coulomb force of attraction when we apply high voltage to this electrode, and here similarly the voltage when we apply, and this is the ground voltage, there will be electric field established in this region, right? Because positive charge will accumulate here, thinking that this is, if high voltage is positive, and negative charges will accumulate on the surface of this electrode similarly. So electric field will be established, and due to this electric field, this electrode, fixed electrode, will attract this movable electrode. Here this is movable electrode and it is attached to a spring, you can see here. So that spring, there is a needle which is attached to the spring like this, and which will move vertically on this scale. So when when the high voltage is applied, the movable plate moves like this. Like this. 3 times I have repeated, it will move only upwards after voltage application. Now similarly, here you can see these two are two plates. This is fixed plate, it cannot rotate. This one is a rotatable plate, and this rotates. So there is a spring attached to this one, which is rigidly connected on one side. On the other side, it is connected to the rotating electrode. This spring, torsional spring it is called. Now, this will also rotate when the voltage is applied here. Like this. So now let us go to next slide. So think a moment on these questions. What is the force on the plates? The first question. And the second one, on which factors this force depend? Third one, how an electrode rotates in electric field when electric field is applied. And the fourth one is, what is rotational torque? And what is the relation between this torque, force, stored energy? So based on these factors, the principles of this are dependent on. Now, what is the force on the plates? So on which factors the force depend? Now let us go to the plates, parallel plates again. Here this is one is fixed, that is movable, and then it is moving in an electric field, and then it is getting attracted to the other electrode. Now consider here I am drawing two parallel planes, and here like this. Now when this plate moves upward a little bit, consider that one. Actually in practice the movement is very small. So up to this distance it has moved. What is the difference? The difference is the stored energy before and after will be different. Now if you consider this element, this differential length as dx. So in this dx, in this volume, the total energy will be lost. This in this volume, whatever, assuming that voltage is kept constant, and then this is HV, this is ground, like this. Now what is that energy? And that energy is related to force, because differentiation of energy dW by dx is force, if you remember. Of course negative sign will be there. We are concerned only with magnitude, with understanding on the direction of the force. So let us recall the fundamentals and then derive quantitatively what is the relation between this force and the applied voltage V, assuming that applied voltage is V. Let me erase everything, and then I will put the equations here, governing equations, and yeah, this is the governing equation. This is the, say, dW is half epsilon E square into A dx. A dx is the differential volume, dW is the differential energy, the energy that is in the small elemental volume, with dx as the width and then A as its area. A dx is the total volume. You may know, I think, half epsilon E square is the energy density in electric field. Now, what is F? F equals to dW by dx. Of course, this is mod. We are concerned with mod only, magnitude only. Half epsilon E square into A, which can be shown to be half epsilon A into V by S whole square. S is the gap. So this is the force on the plates when it is in its position when the electrodes are in their position with S as gap spacing. So, but when there is a movement by X, if this electrode moves by X, say here, then what will be the force due to this spring? Force due to this spring is F is equal to K into X. K is the spring constant. Therefore, this is the governing equation, because when it moves X, the net force on the electrode due to electric field is this, because S minus X you have to do. Of course, sometimes this can be neglected. S is very large and then X is very small in general. S minus X can be directly taken as S only. It doesn't matter. It will a little bit inaccurate result will come. So if you simplify this, you will get this equation. X into S minus X whole square equals to epsilon A into V square by 2K. So this moment of this electrode given by this X is related with this equation. So some nonlinear movement will take place. This scale has to be adjusted. So, but you can see nearly, if you ignore the second order term, X is nearly proportional to V square, not V. So, can we measure polarity of the wave using this? You cannot, because V square. So, negative voltage, positive voltage, the moment will be same. And can we measure, peak value? Is also difficult, because this the movement of the spring, the movement of the electrode is kept very small, and it is a mechanical system, and its time constant is relatively slower than compared to electrical system. So the spring may not respond for high frequencies, and it will be in its equilibrium position. That is why we can measure RMS AC voltages and pure DC voltages, right? So for impulse measurement, this cannot be used, and then other peaks, particular peaks of any other waveforms also we cannot use. So DC and AC RMS voltages, this can be used. Now, what is the, for AC RMS when you are measuring, so V square is, corresponds to what? So the force actually has to be integrated over a period, and that integration leads to integration of V square over a period. So that integration over a period for V square you can get in terms of root mean square. So that's how I am mentioning, whenever V square is there, you can measure the RMS quantity. So this is about this kind of setup where you have one fixed electrode and other movable electrode is moving vertically, right? Now let us erase this, and then let us go to the other kind of electrode where torsional spring is given. Right, this is the torsional spring, and let us see how it moves. This is how it moves in electric field. Now, how this, first of all, how this movement takes place, because you understood, when there are parallel plate, force will be in this direction, and this plate can move upward by some distance if it is allowed to move. But in this case, the distance is kept constant. Distance is fixed now, right? Fixed. But how the force will be exerted on one of the plates to rotate it? How it will rotate? See, unless there is a little bit misalignment, if they are perfectly misaligned to 180 degrees, then the forces are equal and opposite, and then it cannot move. So there should be some small misalignment in one direction, so that in that direction it starts moving. So the forces will be like this, they will be like this, will be attracted. So for example, here you consider this lines of force. So this will attract this electrode and it starts rotating to increase the area of alignment. So like this, I will show you from top view side like this. So initially they are a little bit aligned. Now this alignment will tend to increase, and then depending on the force, because the spring is opposing, this spring is opposing the movement. So depending on the force, a larger amount of the alignment is possible. So this is how. Then how this alignment is related to applied voltage, that we have to see, right? So in this case, what is the energy and how it moves? So here it's not force, it is torque, because it has to rotate now, right? So how torque and energy are related? Please recall that one. So let us see the relation. First let me erase these things. You can see clearly. Again same equation, dW equals to half epsilon E square dA. Here some one assumption is made here, that electric field is uniform and E has been taken. But in fact it is not so, because due to some fringing will be there. So assume that some average effect you are considering or something like that. So half epsilon E square into volume dA into S, right? So here S is constant, I said, the distance between the electrodes. Now dA is variable, and what is area? Area common to two sectors like this, two electrodes. This is consider upper electrode and this is lower electrode. If theta is the angle of alignment, then half theta r square, where r is the radius of this one electrode. So half theta r square is the area. So with that, the differential work dW now becomes half epsilon E square S into half d theta r square for d theta. Then which is equal to 1 by 4 epsilon E square R square S d theta. Now E can be replaced by V by S approximately. This is what is done. Even if it is not visible, it can be easily written like this. Anyway, here it is there. Yeah, the same. Now the torque T of this spring is given by K theta, where K is again the spring constant, which is in magnitude equal to dW by d theta. So this dW by d theta equals to torque. So torque is equals to dW by d theta, this you remember, in magnitude. So equating that, we will get like this. So here in this side, unlike the previous case, you have S minus X. Here we will not get S minus theta because S is fixed. So, and this theta is given by the stable value of theta. This theta is small value incremental theta, please remember. So this is how this will work. The fundamental principle behind this equation, this system is this one. So again here it is the force or torque is proportional to V square. T is proportional to V square. Therefore, in this case also RMS or pure DC voltages can be measured. Now, let us go to next, peaks cannot be, okay, next slide, let us go. This is spring suspension over a pulley. You can see how the system will work. So now can you think how to calculate delta X, the relation between the moment of the electrode, this electrode, and this scale. So these I will give you final result. Okay, you can derive this yourself. What is the relation between movement of electrode and movement of indicator? So this is the relationship. Similarly, this is another system. Similar system. So in this is the main central electrode, and this is the guard ring actually, and a moving disc, this moving electrode. This is called coach spring. So this upper part and then this lower part. This constitutes a spring actually. This is micrometer head to adjust the spring tension and all. And here this is the fixed electrode. So this will work, Let me erase the things first, and then this will work in this fashion. So it will move down, and then here the line of sight from here in this direction, we have to watch how the crosshair changes its position, and based on that we have to find out the reading. Now various electrostatic voltmeters differ in the use of different methods of restoring force. So how the restoring force is done and how it is amplified, all these factors, the differences will depend on. So there are several kinds of suspensions. It can be suspended on one arm of a balance, simple balance, and it's a suspension on a spring, and other use a pendulous or torsional suspension. So in the previous case, you can see here it is a suspension over a pulley, and here in this case in the beginning you have seen several torsional spring, etc. Now let me erase this before going to next thing. So okay, think a moment. Now, what could be the differences between low voltage and high voltage ESVMs, electrostatic voltmeters? And what could be the range of voltages that could be measured using these electrostatic voltmeters? So, the topic of electrostatic voltmeters is split into two parts. This is the end of the part 1, which covers the basic concepts of electrostatic voltmeter. And then in the second part, we will deal with high voltage electrostatic voltmeters and their construction and other details. And then, so stay tuned for the second part.